Alright, so today we're going to be talking about all the different tests for convergence of a series. So let's just get into it. So the first test we're going to be talking about is called the integral test. And for the sake of time, I'm not going to be proving a lot of these tests, even though some of them are provable within like the scope of calculus. But if you want me to prove it, then just let me know and then I can make another video. But the integral test says that let a of n be a sequence of positive terms and we write a of n is equal to some function f of n where f of n is now continuous, positive, and decreasing. So continuous, positive, and decreasing functions kind of look like this, right? Where they're decreasing as we go over, as we increase our x, but they're always above the x-axis. So that's what it means. And when we have some function like that, then the series represented by n is equal to n to infinity of a of n and the integral from n to infinity of f of x dx either both converge or both diverge. So essentially what we're saying is, let's say we have some series and that's each term is represented by a of n, and obviously a series is discrete, right? But if this sequence consists of positive terms, then we can kind of write an analogous continuous version of that sequence and we call that f of x, and f of x must be like by analogy continuous, positive, and decreasing. And now we can see if this integral either converges or diverges, and based on the fact that the integral's convergence or divergence, we can say that the corresponding series, which is discrete. So I'm trying to emphasize the fact that the integral and the series represent different things. The series is summing up discrete values of a of n, where over here, f of x has like values at x equals 0.1, for example, which is like a bogus value for the series. So they converge to different values, but either they both converge or either they both diverge. But the key fact is they don't converge to the same value if they converge or not. But you have this relationship between the integral and the series. So let's apply this integral test. And let's determine, so example. So let's determine whether the sequence from n is equal to 1 to infinity of 1 divided by n root n converges or diverges. Right? And so we want to use the integral test. So another way to represent an integral or a function that takes on these values. So like we're saying that we're going to convert each term n into some function f of n. So analogous function that we're going to be testing for the integral is simply f of x is equal to 1 over the square root of x root x. So the integral test tells us that, well, first of all, this is the same thing as x to the power of negative 3 over 2. And you guys can inspect this, but this is continuous, positive, and decreasing. So we can use the integral test. And I want to emphasize that it's continuous, positive, and decreasing for this range of x is greater than or equal to 1. So that means we can use the integral test. And if this integral from 1 to infinity of x to the power of negative 3 over 2 dx converges, then our original series converges. So if we were to evaluate the antiderivative of this equation, we'd simply get negative 2 times x to the power of negative 1/2 and then we want to evaluate that as limit as b tends to infinity of 1 to b. Now that's the same thing as limit as b tends to infinity of negative 2b to the negative 1 half plus 2 times 1 to the negative 1 half. So that part evaluates simply 2 plus 2, and this is the same thing as negative 2 over b to the 1 half as b tends to infinity. So this denominator will tend towards infinity, and so the entire fraction will tend towards 0. And so we do get that this integral evaluates and converges to 2. And because the integral converges by the integral test, our original series also converges. But note that the value of this series does not necessarily converge to 2. And that's because of the fact that you're basically summing up discrete values over here, whereas the integral is summing up like all the continuous values. So although their convergence and divergence behavior are related, the value that we're converging to is not necessarily the same. And so that was the integral test. And a consequence of the integral test is something called the harmonic series and the p-test. So essentially we can use the integral test to determine convergence on all series of form the sum from some value n is equal to 1 to infinity of 1 divided by n over p, since this will, like, when we kind of make an analogous function as f of x is equal to 1 over x to the power of p, this is always continuous, positive, and decreasing on x is greater than 1. And the other fact is, like, which is kind of more obvious, is that this is decreasing as n is increasing. So decreases as n increases. And so due to these two facts holding, we can use the integral test for all functions in this form. And this form is pretty common, where we have 1 over n to the power of p, and that form is known as form of series, is called the p-series. And we've already seen that, like previously in my improper integral videos, we have seen that the integral of 1 to infinity of 1 over x to the power of p dx converges if p is greater than 1, diverges if p is less than or equal to 1. Because if p is equal to 1, this evaluates to the any derivatives ln of x, and if p is less than 1, whatever any derivative we get, which is another like power function, does not have a converging value on these bounds. And so we have seen this behavior of the integral diverging when p is greater than 1 and p is less than or equal to 1. And so applying this fact and the fact that we have an analogous series, the integral test tells us that if we have a series in this form of n is equal to 1 to infinity of 1 over n to the power of p, because of the fact that we can use the integral test, if p is greater than 1, since the corresponding integral will converge, so does this series. And if p is less than or equal to 1, our series won't converge either. And because of this unique form of 1 over n to the power p, this is also known as the p-series test. And so the p-series test essentially just reinstates this fact that we know from our integrals. something cool about like this p equals 1 is that you get the summation of 1 over n to the power of 1, and this summation from n is equal to 1 to infinity is the harmonic series, because in essentially this harmonic series is known as the barely divergent series, because that is the cusp at which we're gonna barely divergent series. Because if we were to even increase, because in this case, in our harmonic series, p is equal to 1, but let's say we increase p by like 10 to the power of negative 9. So we have p is equal to 1 plus 10 to the power of negative 9. This converges just because of the fact that p is now greater than 1. So because p equals 1 kind of forms the border, the series that forms that border is the harmonic series, and it's also known as a barely divergent series because it's the most slowest diverging series. All right. Uh, Now that we have talked about the p-test, and we have introduced the harmonic series, let's talk about a next new class of tests called the comparison tests. And so the first comparison test is called the limit comparison test. And the limit comparison test essentially states that, well, suppose you have a series determined by the terms a to n, and that's always greater than 0, and b of n is also another. This is another series, so both have their terms greater than 0 for all n greater than or equal to n. So after some value, some finite value n, these series, both these corresponding individual series, always take on values greater than 0, so positive values, right? So what the limit comparison test tells us that if the limit as n tends towards infinity of a of n divided by b of n is equal to some value c, where c is between 0 and infinity, and this should remind you of the limit comparison test that we used for determining whether an integral converges or not. So these tests are very similar to ones we've seen before, so hopefully it's not too confusing. But if we have this case, then our infinite series, with a of n terms, and our infinite series with b of n terms, either both converge or diverge. So this is very similar to our other limit comparison test with integrals, where if both of these kind of both of these have the same sort of order, they'll tend towards, or their limit, the ratio in the limit, the ratio will be some finite non-zero constant. And so that's the case, then either both of these series will converge or diverge. Secondly, if the limit as n tends towards infinity of a of n divided by b of n is equal to 0, that means b of n is necessarily like faster growing. It's bigger than a of n as we go towards infinity, right? So in this case, if the series of b of n converges, then the series of a of n also converges. Again, this is analogous to our integral limit comparison test. And then finally, and hopefully you guys can predict what this will state, if a of n divided by b of n is equal to infinity, so a is like much faster growing, it's like a larger order class of functions, then the series determined by b of n diverges if the series determined by a of n diverges. And the intuition for all these is very similar to the ones for the integral, where like if in this case b of n always takes on smaller values than a of n, and so if a function that takes on bigger values will diverge, then necessarily the or sorry, b of n sorry, I messed this up. Bfn, if the function determined by Bfn diverges, then the function determined by AFN diverges. And when I was talking the arguments, like if Bfn takes on much smaller values than AFN and that diverges, and something that takes on larger values will obviously diverge. In this case, something that takes on larger values converges, right? Bfn is the denominator, and something that takes on smaller values must necessarily converge as well. So that's the limit comparison test. And let's do some examples. So let's determine whether the series from n is equal to 1 to infinity 2n plus 1 divided by n plus 1 squared converges or diverges. So what we need to do is we need to find another function that we know converges or diverges, and then kind of look at the limit behavior between this series and that other series. And so one thing that this reminds me of is the fact that I have a positive, or I have a degree 1 term on the numerator and degree 2 term on the denominator. So this is very similar to, in the limit, this is like very similar to the behavior of this function, 1 over n. And therefore, I hope to compare it with this function. So the limit as n tends towards infinity of 1 over n divided by 2n plus 1 divided by n plus 1 squared. Now I get n plus 1 squared divided by n times 2n plus 1. Now you can notice that the leading denominator in the, or the leading degree in the denominator is also going to be n squared, and the coefficient is going to be like 2n squared, and then over here we're going to have an n squared leading degree, and so our limit is just going to be 1/2. And according to a limit comparison test, since we get a constant that's greater than 0, both these functions will have similar diverging or converging behavior. And we know through the p-test that 1 over n diverges because p over here is 1. And so since 1 over n diverges, this sum also diverges through the limit comparison test. So we know that this diverges. Let's do another example. Let's do the sum from n is equal to 1 to infinity of 1 divided by 2 to the power of n minus 1. So we know that this behaves similar to the or let's just compare the limit as n tends towards infinity of the function 1 over 2 to the n divided by our current function. And then what we're left with is essentially 2 to the n minus 1 divided by the limit as n tends towards infinity of 2 to the n minus 1 divided by 2 to the n, and that's just 1 minus 1 over 2 to the n as n tends towards infinity, and then we're just left with 1 because this term goes to 0. Again, since the ratios are similar, now let's probe the behavior of 1 over 2 to the n, and that's the same thing as 1/2 to the n, and so we're just summing up a series that has this behavior, right? And this is just a geometric series, and we know a geometric series converges. And so since this series converges, so must our original through the limit comparison test, so this also converges. And so the most challenging part about the limit comparison test is finding something to compare with, but hopefully you guys can see patterns of like the functions you want to compare against are just functions that have the main like behavior of the original function but remove like constants like this that just make it more complicated. All right, let's do a few more. Or actually, I think that was yeah, I think that was a good example that of the limit comparison test. So let's work on our second comparison test. So the second comparison test is um, called the direct comparison test. So, and again, this comparison test is very similar to the direct comparison test for integrals. And so the direct comparison test says that let um, the series determined by a of n be or have no negative terms, then our series of a of n converges if there is a convergent series represented by the summation of c of n, with a of n always taking on values less than c of n for all n greater than or equal to some constant n. So after some point, finite point, if c of n always takes on bigger values than the series determined by a of n, and we know that the series determined by c of n converges, it's technically that the fact that this bigger series is an upper bound, and since the upper bound is converging, so must the smaller series, and that's basically what that part is saying. And analogously, our sequence determined by a of n diverges if there is a divergent series d of n of non-negative terms, with a of n always being greater than or equal to d of n after for all n greater than or equal to n. So again, after some finite value of n, if the series of a of n always is like an upper bound on the series of d of n, and we know that smaller series is divergent, then that bigger series that takes on larger values must necessarily be divergent. And so that was the direct comparison test. And I go over an example of it in a previous video, so if you want to see that, just look at that. But those are the comparison tests, and now there's like a few other ad hoc tests that can also help determine convergence or not. And so let us go over those tests. And so the first one of those ad hoc tests are, well, the first of those is called the ratio test. And the ratio test says that let a of n be a series of positive terms. And notice how all of these tests that I've had so far have a precondition of the terms being positive. And that's very important when it comes, like sometimes you have alternating series with negative terms, and then there's only a few other tests that work in those in those settings, and so that's like something that is important to keep in mind. And with limit as n tends to infinity of a of n plus 1 divided by a of n is equal to some value L. Now, if L is less than 1, then series converges. If L is greater than 1, then our series diverges. And finally, if L is equal to 1, inconclusive. So if L is equal to 1, we cannot say anything about divergence or convergence, but on the other cases, we can say whether or not our series diverges or converges. And it kind of makes sense. If our values in the series are getting smaller and smaller, then L will be less than 1. And that kind of like intuitively tells us that we'll hopefully get to a finite sum Whereas if our values of the series get larger and larger, then we're probably not going to be converging to a specific sum. So that was the ratio test. And on that same sort of vein is another test known as the nth root test. And so the nth root test essentially tells us that, so again, we assume that we have the series, the sum of a of n with a of n. This one, we don't have to be positive, but we just have to be non-negative. So each term is greater than 0 for some n greater than or equal to n. So after some point, we only take on non-negative integers. And suppose that the limit as n tends towards infinity of the nth root of a of n. So this comes in handy when our function is like the nth term in our sequence is determined by some power of n. We can take the nth root. And so if the nth root is equal to, well, the limit as n tends towards infinity of the nth root is equal to some value L, the series is convergent if L is less than 1, divergent if L is greater than 0 or infinite, and then inconclusive if L is equal to 1. So very similar structure to the ratio test, but now we're just finding the limit of the nth root of the nth term as n tends towards infinity. So that's the nth root test. And so this can also be very helpful in finding out whether specific series converge or not. And now, before like covering all the tests, the final test that I want to talk about is the alternating series test. So I think if like one thing you guys might have noticed is all the previous tests that I covered have the precondition of the terms being positive, especially after some term n, or always having all positive terms. But not all series will always have positive terms. For example, we can have we can have a series that alternates in value, right? So this is just a geometric series with ratio r is equal to 1/2, and this is an alternating series. And so you can have series that have alternating positive and negative values, and in that case, we don't really have a test right now that tells us whether the series will converge or not. So the alternating series test tells us that a series represented by the sum from n is equal to 1 to infinity of -1 to the power of n plus 1 times u of n. So this -1 to the power of n plus 1 guarantees that our series is alternating. This series converges if all three conditions are satisfied. And these conditions are each u of n is positive. So basically, if I were to remove this -1 to the power of n plus 1, whatever is left over in my function that determines my sequence, that is always positive. And u of n is greater than or equal to u of n plus 1 for all n greater than or equal to n. So after some point, the next term in the series will always be greater than the previous term. And again, I said u of n is positive, so this shouldn't follow. We're removing the negative sign. And finally, the limit as n tends towards infinity of u of n tends to 0. So essentially what we're saying is this this alternating series converges if one, I'm getting decreasing values after some point, and that continues for all n later on, and eventually my terms tend towards zero. And you can, like, one way to illustrate why this is true is, let's say we have an alternating series that starts at some value a, and we're adding u of 1, right? So the first term is like plus u of 1, so we're at this point. The second term is minus u of 2, but it's going to be smaller than u of 1. So we end up here, and then we add a positive term, we then subtract a negative term, add positive, negative, positive, negative. And because of the fact that our each term is smaller and smaller, like the absolute value of each term is smaller and smaller, you can kind of think about the fact that we're kind of converging close to some value L over here, and that's what the series will converge to. And because of this, because we converge to a specific value such as L when we have these conditions help us satisfy, or these conditions, if a series follows these conditions, then that series is convergent. And if you kind of remember the discussion about conditional convergence and non or absolute convergence, then like we can kind of see that an alternating series is a example of a series that can be conditionally convergent, but not absolutely convergent. Because let's say we have the alternating harmonic series, which is just negative 1 to the power of n plus 1 divided by n. You will see that it will follow all of these rules, and you'll get the fact that this is convergent, but it's not absolutely convergent, because to have that series absolutely convergent, we'll need this to be convergent, which obviously is the harmonic series, and that's not going to be convergent. So that is one example, or sorry, this is just one over n. So that is one example of something that's conditionally convergent, but not absolutely convergent. And so we've discussed a lot of these tests. And so what's the order of the test to use when we're given when we want to determine convergence? So procedure to determine convergence. And so roughly, if you follow this procedure, you should be able to tackle any convergence problem. So the first thing you want to do is use the nth term test. I didn't talk about it in this video, but I have another video that talks about it. But you want to use the nth term test, and that tells you if the limit of a of n is essentially 0 as n tends towards infinity. And if that's not true, then we can conclude instantly that we diverge. Now, if it is true, we need to do further testing to determine convergence or not. And we can use like common converging series, such as a geometric series that we know is convergent. So is geometric series, right? And if we're at this point, then if it's yes, then converges, and we know value. If it's not, then the next easiest test to do is the p-test, right? So is p greater than 1? Yes, then converge. And then, or sorry, I should probably just do so is in 1 over n to the power of p form, right? So if yes, then use p-test, and then if not, then we have to use other tests. And in this test, these next set of tests require non-negative terms after some value n, or for all domain, right? So we always need non-negative terms after a while. So we cannot use the like our series cannot be um, alternating in this case, right? And so when this is the case, this is essentially testing for, so these, at this point we're testing for absolute convergence, because even if a even if a series has alternating values where you have positive and negative, you can put in the absolute value, and then all the terms are non-negative, and then you can test for absolute convergence. And because of the fact that we know that if a series is absolutely convergent, it will be convergent, it makes sense to remove all the negativities and just test for absolute convergence first. And so these next set of tests all test for absolute convergence because they require us to have non-negative terms. And so these consist of, so essentially, in to summarize, it tests whether this converges. We test whether this series converges, right? And what we use to do this is we use comparison test. So we add those two comparison tests. Whichever one's easier, we can use that. We can use the integral test. We can use the ratio test or the nth root test. So it really depends on the problem itself. Because depending on the sequence, some of these tests are easier to apply than the others, and it really depends on the problem itself. But depending on problem, one of these tests will tell you whether that series is absolutely convergent. And so if we get convergence, so like convergence, so test is passing, then we can claim convergence. If not, so no slash maybe. So some of these tests like tell you flat out that these series won't converge. For example, like if we had just 1 over n, right, that series, and we use the integral test, we'll get that it doesn't converge. But sometimes we had like -1 to the n of plus 1 over n. Now that will fail the absolute convergence test, but that's not the original function, so it still might converge. And also, you can get indeterminate forms or indeterminate test results when you use some of the ratio test or the nth root test. And so you can either get a no or maybe. And if you get a maybe, then see if you can apply the alternate series test. If alternate series, if not, so the answer is no. The answer is yes over here. So um, if it is, then use result of test, and if pass, then we converge. So this is yes. And if we don't pass, then either we try ad hoc so now at this point we're kind of out of options, so you try ad hoc methods, and these methods can include using telescoping series, so like finding out whether the series was a telescoping series, forming partial sums to converge, etc. So at that, if the alternating series test fails, or if the series itself is not an alternating series, then you must like look for other sort of mathematical ways to either show that we have convergence or show that we're diverging. And some of those examples could be like the telescoping series that I've kind of like talked about before, or kind of forming partial sums in a way that we have either convergence or whether like the partial sums diverge. And one thing to note over here is like at this point, when we're down over here and we start relying on the order in which we're adding up stuff, because everything after absolute convergence, so if we fail the absolute convergence test, that means that we're not absolutely convergent. So at this point, So anything by below this level, you can say if we converge below, then we are conditionally convergent. So anything below that point, we're not absolutely convergent. We're only conditionally convergent, and that is an important point to understand. That although we could be convergent, we won't be absolutely convergent after failing the test for absolute convergence, and therefore that means that if we reorder the terms in the series, we're not necessarily converging to a value. We could be diverging, and that's like one important point to know. So if we ever get to a point where we have to rely on the alternate series test to test for convergence and all the other tests before that test for absolute convergence fail, that implies that we're only conditionally convergent if the alternate series test passes, or if we find out that it's like a telescoping series, or we use like a partial sum method. So that's the kind of roadmap to the procedure to determine convergence. Might seem like a lot, but with practice, it becomes pretty formulaic. And I think like one last thing to note is all of these tests tell us only if we converge or diverge. They don't necessarily tell us what we converge to. Besides the geometric series, that kind of tells us what we converge to. And I guess like when you use a telescoping series, um, we see like what the partial sums kind of add up to. Uh, and that can tell us what we converge to as well. So besides those two, you don't know what you're converging to. You're just telling whether or not you converge.